nanohub.org.
Online simulation and more for nanotechnology.
Welcome to this presentation in the NEED seminar series. So I'm Mark Lundstrom in Electrical and Computer Engineering. This is a seminar sponsored by NEEDS. For those of you who don't know, NEEDS is the electronics part of the Network for Computational Nanotechnology, funded by the National Science Foundation, the organization that created Nano-Hub. And NEEDS has a mission to connect people like Donna, who work on materials and devices, to applications. And she's a great example of what we're trying to do. At our annual review at MIT last May, Donna met Pedro, who's in biomedical engineering here, and the two of them decided together that the device that Donna is going to be speaking about has a potentially interesting application in wireless implantable medical devices. So the two got together, they built a chip already, they're testing it. So that's the kind of thing that NEEDS is aiming to be doing more of. So our speaker today, Donna Weinstein, did her BA in Berkeley, and actually in physics and astrophysics, and then decided to get a little more applied, went to Cornell, did her PhD at Cornell, and I guess RF MEMS, and is now at MIT, running a lab that's devoted to using MEMS to enhance devices and system performance. So we're really delighted to have Donna with us today. Would you join me in welcoming her?
Thanks very much. Thanks, Mark, and thanks, everyone. So it's a pleasure to be here today. I want to talk to you about some of the work that's been going on in our group at MIT over the past 4+ years now. And specifically, I want to talk about RF MEMS resonators and using transistors in order to make these acoustic resonators. Now, the primary motivation behind our work in RF MEMS and MEMS resonators specifically is for frequency sources. Now, frequency sources are necessary for pretty much everything: military, aerospace applications, industrial, automotive, research and metrology, consumer applications. Pretty much everything but the kitchen sink requires a frequency source, right? Well, now with hands-free technology, even your kitchen sink requires a frequency source to measure the capacitance. But there are kind of two ends of the spectrum in terms of frequency sources that you can get today that can be relatively easily implemented in, large-scale consumer applications. On one end of the spectrum, we have quartz crystals, as you can see here. Now, quartz crystals are fantastic. They're basically crystal elastic wave acoustic resonators. They're piezoelectric. I apply a voltage across this crystal, and it strains the crystal, and I can do it at a particular frequency to generate a standing wave. And because they're acoustic resonators, they're very high quality factor. They have very low loss. That translates to low phase noise oscillators, right? Another reason why quartz is a fantastic choice for frequency sources is because it has fantastic thermal stability. So temperature coefficients of frequency of less than 0.1 parts per million across over 100 degrees Celsius are what make it really attractive. The problem is that these are bulky off-chip components, and that limits these things to maybe tens of megahertz in frequency. You can lock these in some phase lock loop to your chip, get up to 35 gigahertz frequency or so. So there's a lot of things you can do, but having that separate chip, having a bulky off-chip component can be a major limiting factor, particularly when you're scaling your system. On the other end of the spectrum, we have LC tanks, inductor capacitor tanks, where you're sloshing not elastic waves, but electrons back and forth between an inductor and a capacitor, right? Now, these are super cheap, right? Both in terms of area, you can fabricate these in the back end metals of your CMOS process. They're intimately integrated with your CMOS, so you don't have to worry about any sort of packaging, routing to the chip, anything like that. The problem is electrical losses are typically much larger than mechanical losses. And so the quality factors of these frequency sources are typically much worse, orders of magnitude worse than mechanical crystals. In addition to that, it's just metals, right? And the thermal expansion coefficient and temperature coefficient of resistance and so forth causes a major problem. And temperature coefficient of frequency of these frequency sources is, in no way comparable to what you can get with these crystals. So really, we want to leverage the best of both of these worlds. We want CMOS integration, but we want high performance that quartz crystals can give you. And we want to scale to very high frequencies of operation, where, bandwidths are much larger, where there's interesting new applications at multi-gigahertz frequencies. Now, people we can see even in the consumer market where MEMS has kind of come in and stepped in to try and get the best of both of these worlds. But what's out there is silicon MEMS resonators that are basically flexural beams, cantilevers or clamped beams, which are driven and sensed using air gap capacitors. You apply a voltage across an air gap capacitor, there's a Coulomb force, it pulls the thing together, right? And you can move these structures that way. They still require their separate processing because these are released structures. Right? And they require, and they're limited to low frequency based on lithography, based on the fact that you have electrical connections from one chip to another, where parasitics will kill you if you try to do this at higher frequency. So our goal in our group is to actually go a step beyond this and really implement completely seamlessly integrated resonators, acoustic resonators, into CMOS. We want to use the silicon because it's high quality factor, so we want front end of line processing of these acoustic resonators. But we don't want to have to deal with any of the packaging, any of the extra processing, any release steps or anything like that. We want to use the existing process and be able to scale to very high frequency and have our resonators side by side with transistors and connect to even at metal 1. So that's, easy peasy, right? How on earth do we do something like that? Well, in CMOS, we have a limited set of materials that we can work with, right? So we don't have access to things like quartz or other materials that are piezoelectric, right, which give us a direct conversion between electrical and mechanical domain. So what we have to work with are capacitors. We have electrostatic transduction capabilities. In fact, we have the best capacitors available, right? The gate dielectric of a transistor. You're not going to find a cleaner, better interface and a thinner dielectric than you can get with that. So in terms of CMOS-friendly ways of driving and sensing acoustic vibrations in these resonators, there's different ways that we could drive and sense these things. Of course, we could make air gap capacitors, just like SiTime and Dacera, who are selling these products in their off-chip components today. But it means we would need to do post-processing. We can use capacitors that still have the dielectric inside and don't need to do post-processing. We have to think of new ways to actually use them. So we can use solid dielectric capacitive transduction to drive or sense acoustic vibrations in the structure. We could go a level beyond. We can even use things like PN junctions we find in the CMOS stack, right? PN junctions have a capacitor built into the PN junction. We can modulate that and generate capacitive forces. We can even sense vibrations across these structures. Other transduction mechanisms include thermal drive, right? So I could run a bunch of current through the device, heat it up, and make it expand, right? Well, that's power consuming. Maybe we don't want to do that. We can take advantage of the piezo-resistive nature of silicon, and do piezo-resistive sensing. We can't drive vibrations this way, but we can sense them. In the same vein as this piezo-resistance, we can actually use the transistors themselves and maybe modulate the channel of a transistor using acoustic waves. So in this work, I'm going to focus on capacitive drive using solid dielectrics, like the beautiful gate dielectric found in CMOS, and transistor sensing that really leverage the best of CMOS to get to very high frequency operation. Okay, so let's take a step back. Let's first take a look at the solid dielectric driving of acoustic resonators. So this is something we started before looking at CMOS. And what you see here is basically, right, in the case of silicon resonators, we can have a suspended structure which we want to vibrate, or we want to move, right? We can put an electrode next to it, separated by some air gap, right? And apply a voltage and get vibrations, right? On the other side, if I have vibrations in the structure and I have a voltage across this capacitor, well, the capacitance is changing as this beam is moving, and I can detect a current at the output, right? Well, if we fill in that air gap with a dielectric, we can still do the same thing, but now instead of measuring displacement, we're measuring strain, right? This film is squeezing, expanding and contracting as this thing is vibrating. But we have to have that capacitor built into the resonator itself. So what you see here is a silicon bar resonator. So it's expanding and contracting in this direction in the plane of the wafer so that I can lithographically define different frequencies on a single chip, which we want to be able to do. And so basically almost everything here you see is silicon, except for these two bright lines here, which are actually sandwiched dielectrics inside this resonator. And so if we cleave along, along this edge here and look from the side, you can see a 15 nanometer nitride film, which is sandwiched between the outer part of the resonator and the inner part. Right? And we can apply a voltage across that, strain the film, and launch these acoustic waves in the structure. So with these kinds of devices, we were able to demonstrate the highest frequencies in silicon at that time. This was back in 2009. So we showed up to 6.2 gigahertz acoustic resonance. That was, roughly 6 times better than any other resonator out there in silicon. And we also showed that they had fantastic frequency quality factor products, FQ products. This is an important figure of merit for oscillators, right? And for getting low phase noise in oscillators. Another interesting feature was that the motional impedance, which is basically the ratio of the input voltage to output current, right? So as a MEMS designer, I want to reduce the motional impedance as much as possible so I get a large signal out for some signal in. That motional impedance actually improved as we scaled to higher frequency. And this was very unique to these structures, and it showed a real promise for scaling MEMS resonators to multi-gigahertz frequencies. But I'm totally cheating here. What I'm showing you for the frequency response of all of these different resonant peaks is the scalar conversion to 1, SC to 1. For those of you who don't speak RF measurement, this is, normally you would think, okay, in order to look at the frequency response, basically the transfer function of a resonant structure, I apply an RF signal in and I look for an RF signal out. And I'm going to have some peak, right, corresponding to the resonance. Well, the problem is as you scale to high frequency, the capacitive feed-through between drive and sense becomes such a problem that your signal is completely inundated by electrical feed-through. And so that's a big problem for scaling to high frequency using these passive devices. And in order to deal with it, in order to be able to measure the mechanical behavior, we had to use the fact that the capacitor acts as a mixer. And in terms of the driving force being proportional to the square of the voltage. And we actually applied an LO signal across one side and an RF signal on the other. So we could measure at the other port at another frequency. So we get only the mechanical signal, not the feed-through. So that's all well and good for studying these devices, but in terms of getting a self-sustaining oscillator with small footprint and low power consumption built in CMOS and used as, say, a clock, well, I really don't want to require an LO in order to make my oscillator in the first place. So I really need a way to do 2-port measurement, RF in, RF out, for these kinds of resonators. right? So what do? Well, what we need is to change the way we sense the vibrations in the structure. So we need to decouple this input electrically from the output. And what we did was we took this bar resonator and we stuck a transistor inside of it. So what you see here is a diagram of that same bar resonator, still silicon resonator, top view. Now it's expanding and contracting in this direction. So you have elastic waves going up and down here. And here's my two nitride films, which are sandwiched inside. And all this dark blue that you see here is highly doped. Let's call it N+. And I'm going to leave this middle part undoped so that I can form a transistor. So now it looks like a weirdly deformed split gate FinFET, right? Where my fin is actually some weird shape corresponding to my resonant cavity, where the length here defines the resonance frequency. So what can I do? I have two gates, and source and drain. So here's my two gates, source and drain. I can bias one gate into accumulation so that no current flows between the source and the drain on that side, but I can generate a charge in order to generate a capacitive force and drive acoustic vibrations in the structure just as we had in the other passive device. On the sensing side, I can bias this gate into inversion. So I get a channel formed here and a drain current flowing near this interface with the dielectric. So now as I have elastic waves expanding and contracting this structure, right, I'm actually modulating the strain as seen by the channel of the transistor. And I'm piezo-resistively modulating the mobility of the carriers. So what I can get out is actually a modulated drain current at the output of the transistor, which actually gives me, which has a mechanical response. So what I've done is decoupled my input drive from my output sensing in a new way. For the device people among you, a basic model of this structure looks something like this. We had to come up with a new symbol. Looks kind of like a crystal, kind of like a transistor, pretty cool. All right, but it's a 4-terminal device. So here I have my drive gate, gate 1, which is basically applying a voltage across a capacitor and generating an RLC resonance, essentially mass spring damper system, right? On the sensing side, however, I have something that looks like a transistor. But instead of a normal transconductance, which of the transistor, which depends on the voltage applied at this gate here, this is now kept at a DC bias, no AC signal on it. I have instead a piezo-resistive transconductance, an electromechanical transconductance, which depends not on the input voltage, but on a voltage across this capacitor, which is really just a spring. So it corresponds to displacement or strain in the structure. So I have here an electromechanical transconductance, which amplifies my mechanical signal prior to any of these parasitics that kill us at high frequency. So we can measure at much higher frequency than possible before. So that's the basic idea of the resonant body transistor. And these were these first generation devices that we used to demonstrate this structure. These were built in-house. And what you see here is that same structure, gates, source, drain, and it's expanding and contracting in this direction. And we demonstrated up to 37 gigahertz acoustic resonance with frequency quality factor products comparable to those at lower frequency. So actually still among the highest in silicon to that date. And this was about an order of magnitude higher frequency than ever done before. And the reason we weren't able to detect frequencies higher than this was because the FT of the transistor, which is a crappy transistor, we built it in-house, remember? 15 nanometers of silicon nitride gate dielectric, W over L of like half, okay? And someone etched Pyrex in the tool prior to it being used to etch the device layer. Extremely shameful. The reason we couldn't do that is because the FT was 40 gigahertz, right? So if you get better transistors, higher gain transistors, higher FT transistors, you improve the performance of the device. take that coupled with the fact that the yield of this process was 2, there they are, you're looking at them, we really wanted to leverage the CMOS process, which is a high yield, high performance process, right? So we wanted to do this in CMOS. Now, people have done CMOS MEMS before, and they're working on it now still, but it always involves post-processing, a release step to freely suspend structures and have these air gap capacitive resonators. People have used back end of line materials, the metals, the oxides or low-K dielectrics that are available in the back end process in order to suspend beams and make metal resonators, make variable capacitors, accelerometers even, using back end processing. And what they do is they etch away passivation around the structure to freely suspend it and etch away underneath the device. We really want to use silicon. We want high quality factor, high temperature materials. So we want front end of line processing. People have done front end processing in CMOS as well. What you see here are polysilicon beams using something like a gate dielectric. This is in TSMC, I think 180 nanometer process, where they have a couple extra poly layers for capacitors. And these beams have air gap capacitors to drive and sense on either side. But if we were to take our, high yield, high gain transistors, which we want to leverage from CMOS, and we were to release them and do this post-processing on them, well, we wouldn't really have the high yield, high performance anymore. A lot of pain has gone into, by the foundry has gone into perfecting these devices, which include silicides and stress liners and all sorts of things that when you freely suspend a structure, you completely alter or damage. And so what we wanted to do was have a completely unreleased structure. What you see here is a cross-section of a hypothetical CMOS stack, in this case SOI, so we have an buried oxide layer underneath. And at the transistor level, we can pattern the silicon and pattern materials around the structure, say vias or metal layers, in order to confine acoustic vibrations in this solid medium. And we can have this side by side with transistors, right? Really at the front end process. So that was the vision here. Now, in order to get acoustic confinement in this essentially non-homogeneous medium, right, what can we do? So we decided to take a page out of the book of Acoustic Bragg Reflectors, or Bragg Reflectors. They've been around for a little while. You can actually get there are commercially available resonators using acoustic Bragg reflectors. What you see here is a solidly mounted resonator. This is a piezoelectric film sitting on top of a substrate, so it's not released, right? And to get the acoustic confinement, what they do is they pattern high and low acoustic impedance materials, in this case tungsten and oxide, in order to get, at a particular frequency, a very good acoustic mirror. This is completely analogous to optical Bragg reflectors, or Bragg mirrors, which are used for, dielectric mirrors in low loss systems. The problem with this structure is that you still have 5 out of 6 faces that are exposed to air, so you still need to package the structure hermetically. And this entire thing, you're depositing these materials, and the thickness of those materials defines the frequency of your structure. So you can't have multiple frequencies on a single chip, actually even on a single wafer, right? Which we want in order to have these flexible multi-frequency systems. So we kind of took this thing and kind of looked at it on its side, right? And we formed acoustic Bragg reflectors in the dimension of the wafer, and lithographically defined. This was our first run of CMOS acoustic resonators. We did this in IBM's 32 nanometer SOI process. What you see here is a Frankensteined transistor. We took the transistor available from the CMOS foundry, from the design kit. We changed geometries, silicon layer, doping layers. We added a capacitor on the silicon island in order to drive acoustic vibrations. So what you see here is a drive capacitor for launching acoustic waves in this silicon bar. This thing is surrounded by oxide. This is shallow trench isolation, defining the silicon islands. And the structure is formed from polysilicon gate and silicon device layer with the gate dielectric sandwiched inside of it. So we can launch acoustic vibrations with this capacitor, and once these vibrations are established at resonance, you can detect using a transistor on the same island. And that's, remember, piezo-resistive sensing of these vibrations. You can see in this SEM, here's the resonant cavity if we cut here. Using silicon and polysilicon layers, oxide surrounding it, and then acoustic Bragg reflectors using the same material stack on either side. There's identical side on this. What we also saw was actually some wonderful metal Bragg reflectors, or phonic crystals, which got formed. These were not intentional. These are formed using the CMP fill step, which the foundry puts in for you, which we only found out after we got the chips back. That was the first process. There's ways to get rid of it, or to manipulate it to do what you want. But we actually, we got acoustic resonance is supposed to be defined in this direction. We got some fantastic resonances in this direction as well. As you can see here, here's the frequency response of this device. You can see all these, you can see the resonance designed at, 11 gigahertz and some great spurious modes all around the structure. So because of that, because of the fact that we were learning about the material properties of this stack, right? We got a quality factor of around 30. At 11 gigahertz. Now that's great for LC tanks. For acoustic resonators, you could do at least a couple orders of magnitude better. Also, we wanted to get rid of these spurious modes, and a large feed-through, which actually happened due to capacitive feed-through through the silicon and directly from drive to gate. So these are things that we wanted to improve on for the second run. But one thing we got for free out of this process was passive temperature compensation. So typically, silicon has temperature coefficient of frequency, TCF, right, which is roughly minus 30 ppm per Kelvin. Okay. And in order to compensate this temperature coefficient of frequency, people do a couple different things. Either you can correct for it with, say, ovenized systems, depending on how much you want to pay for your oscillator and how much you care. But there's also passive ways to compensate. You can actually use oxide, silicon dioxide, to form a passive temperature compensation, leveraging the fact that silicon and silicon dioxide have opposite temperature coefficient of Young's modulus. So with the right balance of these materials, you can actually cancel out the effect from silicon with the effect from oxide and get a very thermally stable resonator. Well, we get that for free. We have a silicon resonator. It's surrounded by oxide, right? So even without trying to engineer for this, we were just trying to engineer for particular frequency and for good quality factor. We were able to measure temperature coefficient of frequency under 3 ppm per Kelvin. And some resonant modes actually showed sub ppm per Kelvin temperature coefficient of frequency. Which is fantastic for making stable frequency sources. So that's a really nice feature of these unreleased resonators. But we really wanted better performance, right? We wanted a higher quality factor. We wanted fewer spurious modes. So we started looking around and seeing what else can the CMOS stack provide me, right? And one of the things that we got very excited about was IBM's deep trench capacitors. They're these beautiful high aspect ratio capacitors that are typically used for DRAM in their process. And so we thought, well, we can actually use these both to drive acoustic vibrations, but also to form these periodic structures and get acoustic reflectors in the silicon. Right? So we taped those out in IBM, but we also, well, IBM takes about 9 months to get a chip back to you. So in the process, we actually fabricated some of these types of structures at MIT. Now, not as high aspect ratio, of course, and not as beautiful as IBM's process, but still demonstrating the concept. What you see here is these deep trench capacitors that have, in this case, a nitride conformal film to form the capacitor, and they're backfilled with polysilicon. So we have a capacitor formed inside the structure, right, for solid dielectric drive. But we can also use those same trenches to form these acoustic reflectors, right? Where we're leveraging the small acoustic impedance mismatch between bulk silicon and polysilicon in order to get the reflections. And with these devices, we demonstrated quality factors over 2,000 at 3 gigahertz. So these were really promising in terms of the performance of unreleased resonators. This was the best performance at that time. We were the only ones really working on fully unreleased resonators. So that's all well and good, but then you go and talk to Intel, talk to circuit designers, talk to TSMC, and they all say, you know, we really don't use IBM's SOI process for what we do, right? We use bulk CMOS, right? And we don't have deep trench capacitors, so what can you do for us? Well, the question is, how can we get acoustic confinement in bulk CMOS, right? The answer is leveraging what's above you. So I can't really do anything in terms of what the CMOS stack has to offer me underneath the transistor. It's just silicon. And if I'm not careful, I'm going to be driving these acoustic vibrations with this capacitor, which is the gate dielectric, and I'm just going to be launching these waves straight into the substrate and losing half my signal even to start with, right? So that's extremely painful. What I need to do is find modes that can be confined in this, in the top of the silicon. And all I really have to work with me is the maybe shallow trench isolation and vias and routing, right? So we can actually use the vias around and above the structure, above the transistors, in order to form not one-dimensional acoustic Bragg reflectors, but 2D and 3D phononic crystals, right? Which have particular band gaps, right, based on their spacing. And if I define that band gap, I can define a region where at a particular frequency range, elastic waves cannot be transmitted through. So they're going to be reflected back down onto the transistor. And I can do that coherently. So we can find these modes in these more complicated structures, which involve maybe several metal layers, leveraging both vias above the structure as well as vias on the side, and the transistors for driving and sensing are all in here in the middle, in the resonant cavity. And we can get high quality factor, high amplitude vibrations resonators. So this is actually what we taped out with Pedro's group through the NEEDS program in order to get low high quality factor, small footprint, low power resonators for oscillators, for transceivers, for implantable sensors. There we go. All right, so that's step one of the process. Okay. So in terms of silicon CMOS resonators, this is where we stand, and it's very promising first results, and we're going to keep pursuing this and push into the application space, because the idea is I've got these devices I can plop into layout, send off to the foundry, and get back as a complete process, no post processing or packaging. So silicon gives us high quality factor, it gives us CMOS integration, and we can leverage the mature CMOS technology. The problem with it is that it's not good for everything. The efficiency of transduction from the electrical to mechanical domain, transduction of energy in silicon, basically using electrostatic transduction, using capacitors, is not so efficient, right? And that just is defined by how much energy I can store in a capacitor. In order to get very low loss resonators, I I can only push electrostatics so much. And in that case, I want to start looking at other materials. If I really need a low-loss system, say in the case of front-end filters for your radio, right? I need a low-loss system which maybe uses piezoelectric materials. As I mentioned, quartz, right? Well, actually, quartz is roughly has roughly the same transduction efficiency as electrostatics. It's pretty bad. It was chosen for its temperature coefficient of frequency. But there's a lot of materials out there which have very high piezoelectric coefficients, right? Very good transduction efficiency from one energy domain to another. Aluminum nitride is a common a piezoelectric material, which maybe you've heard of. You all have in your cell phones right now, most of you, in the form of an FBAR, film bulk acoustic resonator. And those are used for your filters, for your front end right now. Well, aluminum nitride, is still going to have the same problems as all these passive resonators, that when I scale to higher frequency, I'm dominated by feed-through. So I still want to use the active sensing mechanisms, basically the transistor as a sensing element for my acoustic vibrations in order to be able to scale to higher frequencies of operation. So for that, I need a piezoelectric material in a material process or in a technology platform that has transistors, and preferably high-frequency transistors. And actually, for filters, you want high power as well for large power handling. And the best such platform is gallium nitride. So gallium nitride is a 3-5 semiconductor. It's wide band gap, right? It's similar in performance to aluminum nitride, except it's a semiconductor, and I can get these HEMTs, high electron mobility transistors, built into it. Right? And that leverages 2D electron gas, right? That forms the channel of the transistor in a GaN-AlGaN heterostructure. So that's the typical gallium nitride transistor, looks something like that. So in terms of the transduction efficiency, I can get something comparable to aluminum nitride, which is the commercial god right now in terms of piezoelectric filters. And I can get quality factors which are almost on the order of silicon. In fact, I can get frequency quality factors on the order of silicon, and even better if I get the material growth down. And so as the millimeter wave IC technology in gallium nitride matures, that will only get better with time. So once I get this technology platform for millimeter wave ICs with high quality factor resonators, I can think not only about frequency sources, but about filters. And using gallium nitride, I can actually, and I'll talk about this in a moment, I can actually configure those filters, turn them on and off, which is not possible with any other piezoelectric material out there. And I can think about channelized radio architectures that switch between filters, allowing us to be able to configure front-end radios very easily, right? There's a big program, a big effort here. Of course, Dimitri Peroulis is working on this. Bill Chappell's working on this over here. And I can use these filters at the front end, really connected to the antenna, to alleviate the linearity constraints on my following LNA, on my amplifier, and be able to span a broad range of frequencies, right? And be able to pick out interferers when I don't want them, and so forth. In that vein, we can think about, ad hoc configurable radio, where depending on the environment, right, let's think about a friendly environment where I'm just trying to get to download, or stream video faster. And I've got all of these different standards available to me, but I can really only work with one at a time because I've only got one radio, right? If I have a configurable radio, maybe I can leverage different standards whenever they're available, depending on the environment, and get the most out of the frequency spectrum. right? On the other hand, you know, if you're DoD, then, well, we've got interferers, and people are out to jam our signals, and we can actually notch out, right, filter out whatever interferers are trying to jam the radio transmission, and we can get around in hostile environments and communicate in hostile environments. So, depends who you're talking to. Okay, what do these structures look like? Well, again, we're leveraging the benefits of transistor sensing of acoustic vibrations. So before I had a capacitive drive and a FET sensing on this resonant cavity, right? So now, gallium nitride is piezoelectric. I want to leverage that, right? So instead of capacitive drive, I can generate fields in this aluminum gallium nitride and gallium nitride stack, and piezoelectrically excite vibrations in the structure. So let's say I have an electrode for that on this suspended bar resonator. On the other side of that suspended bar, I can have, instead of a field effect transistor, I can have a HEMT, right? A high electron mobility transistor, where I get source, drain, and gate on top, right? And the 2D electron gas formed between the GaN and the AlGaN to conduct current through it and form the channel. I can do that with either released devices, as in this structure here, or I can leverage, again, the same acoustic confinement methods in order to make unreleased devices, as you can see here, right? And we can fill in regions with, say, silicon nitride passivation, possibly alumina passivation, as we learned that may give you much better stability in terms of your HEMTs. And we can actually, this has several benefits because primarily the thermal conductivity of a release structure is pretty bad, right? So if I have a transistor running through this, I have heating in the device. That heating is going to affect both the transistor performance. It's also going to affect the temperature of my resonator in terms of frequency, right? So if I can dissipate heat, I can have linearity over a much larger power range, right? Which is important for filters. Okay. I want to mention one element of these gallium nitride resonators, which is really rather unique. And that's the use of the 2D electron gas for transduction, for driving and for sensing. So the heterostructure that is used for gallium nitride resonators, as I mentioned before, is gallium nitride followed by aluminum gallium nitride. Those form a potential well where electrons like to sit, so they're confined in this 2D plane, and you can conduct it. Basically, it's a sheet of conductivity which is physically not there, right? It's formed by this potential well formed by the bands of this heterostructure. So if I can actually access that 2D electron gas, which I know I can using, say, source or drain contacts available in the process, I can actually form an electrode using this invisible electrode, right, this 2D electron gas. And I can actually form a capacitor between, say, a Schottky contact on top and the 2D electron gas. That capacitor, I can get fields. Fields mean strain in a piezoelectric material, and I can drive acoustic vibrations. So if I have a transducer that looks like this, I can actually leverage the fact that this 2D electron gas can be depleted away when I don't want it. I mean, this is how you turn off a transistor in the HEMT process. You apply a DC voltage in this case, negative, right, to the Schottky gate and deplete away the 2D electron gas, right? Deplete away the electrons. If I don't have electrons there, I don't have an electrode. If I don't have an electrode, I don't have fields to drive acoustic vibrations. Similarly, I can do this for sensing, right? So this is the first implementation of a piezoelectric material where you can actually use a DC bias to switch off the transduction. This was one of the cons of piezoelectric material, why some people choose to use electrostatics and even though it's less efficient, right? Because you can actually have DC control of the transduction and turn off the vibrations when you don't want them, right? And so this is the first such implementation in a piezoelectric material. So that's very exciting, because now I can think about those configurable filters in the front end radio, right? And I can apply a DC bias out of line of the RF signal, so we're not degrading the RF signal, right? And we can actually switch off the filter when we don't want it with very good isolation. So that switching mechanism, right? So if I have this resonator, I can think of, say, applying this DC bias to the drive electrode, right? And depleting away the 2D electron gas. And I can turn off transduction that way. In addition to that, I can actually turn off the HEMT, right? If I'm sensing on this HEMT, and I'm sensing now instead of piezo-resistive modulation of the drain current, I have piezoelectric modulation of the drain current. Well, if I turn off the current, then I don't have a signal, right? So I can get 10 to the 5x suppression of my signal when I just apply DC biases to turn off the device. So I can get very good isolation in the off state. So that's a very nice feature. Another really nice feature of this depletion of the 2D electron gas, when I don't want to use the device, is imagine in that filter bank, right? I have all these filters, different frequencies. And in order to span a broad range of frequencies so that my radio can be wide band, I need a lot of filters, right? And they're all connected to my antenna. And they're all loading my antenna capacitively. Well, when I deplete away this input capacitance, I'm reducing it, and it doesn't completely go away. It's roughly an order of magnitude reduction in capacitance. But what it means is that I can have 10 times more filters in my filter bank. I can span 10 times the frequency range as I could before with the same capacitive load on the antenna. So that's a really powerful thing. It's been a major showstopper for these filter banks at these narrow band filters at the RF front end, because that capacitive loading can actually kill you. So this is a really nice way to turn off the capacitance of filters or bands that are not in use. So we demonstrated this switching of these piezoelectric films in released GaN resonators. We showed both passive devices where you have piezoelectric drive, piezoelectric sense, and we were able to show these at lower frequencies, say 250 megahertz, and you see that with just turning off one of these transducers, so just the drive transducer, we apply -7 volts, the threshold voltage in the MMIC technology. And we're able to get 19 dB suppression of the signal. Of course, we can get even better than that if we deplete away the 2deg on the sense side as well, right? So this is very nice. Frequency quality factor products of 10 to the 12. So that's about 1 order of magnitude lower than silicon, but much higher than you could do with most technologies out there now. And in order to go to higher frequency, right, we want transistor sensing, we want active sensing. So for higher frequency applications, we used piezoelectric drive and HEMT sensing in these structures. In this case, the vibrations look like this. It is essentially expanding and contracting in the plane of the wafer. And we were able to show acoustic resonance up to 3.5 gigahertz and complete suppression of the vibrations. We didn't turn off the transistor in this case, only the DC bias on the drive side to deplete away the electrode. And so this off switching is a really nice feature, and we measured a 13x reduction in the capacitance at the input in doing so. The 2deg is also a really nice feature to help us study the properties of gallium nitride mechanically. So all these metal electrodes affect the performance of the resonator. Metal is, of course, more lossy than these single crystal semiconductors. There's phonon electron scattering. There's an interface between the gallium nitride and the metal, which actually contains gold in this case. which means that there are stress gradients at these interfaces, and that translates to loss as well. There's deformation of the mode. And so it's hard to get out of, for example, these quality factors to extract out how much is really the fundamental performance of the gallium nitride and how much of it is due to the fact that I have these metal electrodes. So we're able to, instead of using metal electrodes on top to play with the gallium nitride 2-deg below, we can actually pattern the aluminum gallium nitride sitting on top of the GaN in order to pattern the 2D electron gas itself. And we can make electrodes using only the 2D electron gas, which means there's no metal involved at all on the resonator. And using that, we can interrogate the fundamental properties of gallium nitride, which turn out to be a little bit better than the previous devices, but certainly not in order of magnitude. This tells us that we need to work with the growers to improve the quality of the gallium nitride, and specifically the gallium nitride buffer layer with all those dislocations. Dislocations mean phonon scattering is loss, right? So that affects the quality factor of the device. So we can now, using this tool, iterate back and forth with the grower, in our case, Raytheon, in order to improve the quality of the gallium nitride and study it fundamentally. All right, so with this platform, right, we can really leverage ICs, or IC technology, whether it's CMOS, whether it's GaN mimics, whether it's something else, whatever comes up, to make high-frequency resonators. Now, these high-frequency, high-quality factor resonators in CMOS are great for frequency sources, for clocking applications, even for wireless, just not filter front ends, right? And even for higher frequency applications, once you get to, say, 94 gigahertz, you start talking about personal navigation, imaging. There's a lot of things you can access at higher frequencies that just have not been available before, right? And they require new interesting circuit topologies to really leverage the performance of these devices. So that's an interesting area to look into. But once we get away from silicon, say go into gallium nitride, we can even offer configurable filters and look in that space, in addition to the frequency sources, which now can be done in gallium nitride as well. And you can get into switchable filters, cognitive radio, and so forth. There's, of course, other applications, sensors, which I haven't even started going into, where, both of these technologies can really leverage these devices for sensor applications, thermal sensors, physical sensors, accelerometers, gyroscopes, and really leverage a solid transduction, a solid state transduction, in order to get robust and high sensitivity, high frequency systems. Okay, let me acknowledge the people who do the real work. These are the students working on these projects, and support from DARPA, NSF, SRC, Intel, and Raytheon, with whom we collaborate on the gallium nitride. At this point, I'll be happy to take any questions.
Two-part question, if you don't mind. I was wondering if you could comment a little bit on the linearity of some of these resonators. The test conditions are such that maybe you're not dropping a ton of power across the test configuration.
Yeah.
Maybe a follow-up to that also. If you could talk a little bit if you thought of some clever ways to tune some of these resonators from a frequency point of view, especially given that structural acoustics of that frequency is likely to be a bit black magic. So.
You mean targeting the right frequency at the...
Tuning it after a device is actually made. Right?
Oh, yeah, okay. Yeah, sure. First question was on?
On linearity.
Linearity, okay. So in terms of the linearity, for electrostatic devices and dielectric transduction, so the driving force is proportional to voltage squared. So already we have a large IIP2 point, okay? We can't ignore that. In terms of taking taking that term out, the linearity is very good. That's because the strains that we're inducing, we're really not subject to the same nonlinearities as air gap devices which have large displacements and the force proportional to 1 over gap squared. And so you have this stiffness, electrical stiffness problem. So we don't have that same problem. We don't see, when we pump up the power, we don't get a frequency shift in the same way as air gap devices. And really the limiting point in terms of power handling becomes the breakdown of the dielectric. But we do have this second order nonlinearity, which just cannot be ignored. In terms of the gallium nitride, it's extremely linear. Haven't shown it here, but there have been measurements that have shown gallium nitride IIP 3 points above 30 dBm. And that's because it's a high power material. You can get high fields, and the limiting point in terms of the third order nonlinearity is self-heating. So actually, those were in released devices. If we make these unreleased devices in gallium nitride, it should be better than that. Yeah. So the second question was tuning. Yes. Oh, tuning. So trimming due to fabrication variations. So, okay.
Or even hitting your frequency target that you set.
Hitting the frequency target that you set. Yeah, okay. So that's a great question. Tuning is always the holy grail of MEMS resonators, and it's always a complete trade-off between quality factor and tuning. I take that back. You can pump a bunch of current through the device, heat it up, and tune it about 1% that way. People have done that and have written papers about it, and that's all well and good, as long as you're okay running milliamps through this thing, and that's obviously power consumption. But it also means that you have to design a resonator which is very temperature sensitive, and we're doing everything we can to get temperature stability. So I would say that actually that's not a good idea for what we're trying to do. Leveraging high yield, high performance processes like CMOS means that we can get very low fabrication variations from device to device though, and once we have designed and optimized at a particular frequency, we can actually hit it pretty well. So measuring same devices across different dies, even from different wafers, we saw something like 0.5% variation in frequency across identical devices. Yeah. But yeah, tuning, I would say we have small devices, put a lot of them, and swap between them. But for trimming, right, so that's for tuning. For trimming, it's a different story. And you just have to get the fabrication process down. Yeah. Mm-hmm. Yeah.
I have a question about bulk CMOS resonators. So do you have any characterization data on how much of resonance power leaks through the bulk of the CMOS? Because when you see the clocking circuits like PLL and other circuits, the substrate noise is a major bottleneck there.
Well, so the first measurements on bulk CMOS were done this weekend, so we don't have that data yet. So Bichoy here is working on both taping out the real devices, but also simulating and optimizing them. And there are ways for us to predict those loss mechanisms into the substrate, and also the even signal crosstalk between them. So that's something that we can develop. Yeah, you can play around with things like deep N wells, and there's ways to get better isolation, both electrically and mechanically, as needed. Yeah.
Can you compare the phase noise of your bulk silicon versus HEMT?
Yeah, no, so we haven't done that characterization yet. Yeah, obviously it's going to be limited by the phase noise of the transistor, and so that's technology dependent. Yeah, but we haven't done those measurements for these devices. And those HEMTs were fabricated at MIT, so they're, yeah, not that great yet. Yeah.
What's the expectation about the power handling of this kind of resonator?
Yeah, so as I mentioned, for the power handling in electrostatic devices, you're limited to essentially breakdown of the dielectric. So whatever fields you can get across your dielectric without leaking. In gallium nitride, it's over 30 dBm as measured now, and limited by self-heating. Mm-hmm. Those measurements were done at Michigan. Mina Raizadeh has a GaN resonator showing that. Mm-hmm.
Any other questions?
Excuse me, how do you do CMOS process? How do you get rid of those metal particulars over the metallization limit?
So that's really just in the layout. Get rid of them, you mean?
Yeah.
There's a CMP exclude layer you have to apply. You just.
But it only covers a very small space.
That's right. So, but our devices are 3 by 5 microns. So they're small enough that that's not an issue. But yeah, you do, so you probably don't want to get rid of it everywhere, but you want to kind of place your metal in a specific way that you know what the acoustic reflections are going to be associated with that, which is, of course, the route that we're going to get even better confinement using those metals. Yeah.
Okay.
Great.
Thanks again.
Thanks, everyone. Thank you.